Hello and welcome to PyData Global and to my talk on Thrifty machine learning. This talk is going to be about how to cultivate more economical and cost-conscious modeling habits for machine learning practitioners and data science teams. There are three sections of the talk. The first section of the talk is about where machine learning has been the last 5 years, 5 to 10 years in the applied kind of commercial machine learning space. The second part of the talk is going to be about how to be thriftier in our machine learning practices. And then the end of the talk is a bit of a thought experiment, which I hope you'll join me on, thinking about how things might change if we shifted our perspective in terms of the goals of machine learning towards sort of a more cost-conscious, thrifty perspective. So first, to introduce myself, my name is Dr. Rebecca Bilbro. I live on the East Coast of the United States of America, and I work at a company called Unisys, where I do applied machine learning. I'm also the author of the book Applied Text Analysis with Python, which is an O'Reilly book, and I'm the creator and maintainer of the Python Yellowbrick library, which is a library for doing machine learning diagnostics for data scientists. If you're looking for me on any of the social platforms, I am Rebecca Bilbro, kind of on every platform, so I'm pretty easy to find. So in terms of where we find ourselves these days, the phrase for me that comes to mind is the phrase, an embarrassment of riches. And when I think about this phrase, the imagery that comes to mind are chandeliers and flutes of champagne and the Great Gatsby and fancy things. What an embarrassment of riches means is, a time where you have more than you need. There's an overabundance of things. And I think that actually is a pretty apt description of where we have found ourselves in the last few years of doing machine learning in an applied context. And if you think about what has really caused this overabundance, I think really one of the main answers is open source software. We have never had more open source software than we do right now, and we've never had access to more machine learning code in the open than we've ever had before. There are new machine learning libraries that come out all the time that can help us do specialized types of models to assess the quality of our models and assist us with the diagnostics process, like Yellowbrick. But there's really never been more open source software than there is right now. We've also never had access to more compute resources than we do at this very moment. Whether that is kind of running code on CPUs in your laptop, or if you have sort of a custom rig that you've built for doing machine learning that has souped up with GPUs, or if you have access to the company credit card and you are running code on very expensive TPUs in the cloud, these are all, at least theoretically, kind of realistic ways of doing machine learning these days. And then the other thing is we've never had access to more opinions than we do right now, right? We've never had access to more ideas and opinions about how we should be doing machine learning, how we should be spending our time doing machine learning and spending our resources and our money doing machine learning, whether that is, reading the archive or exploring kind of Q&A on Reddit or Kaggle or Stack Overflow. If you are reading articles on Medium, we have kind of this overabundance of opinions about how we should be using open source software and how we should be using those compute resources. Unfortunately, this sort of confluence of abundance, has led to, I think, some practices that are not particularly efficient when it comes to time and money. There's this expression, a fool and their money are soon parted, right? And I think that in the next few years, for people who have not already started to experience the kind of economic impacts of COVID-19, many of us are going to start feeling these, and we're going to start feeling them on machine learning teams, particularly at companies where there's been some kind of discretionary budget, that sort of imagined, well, if we let the data scientists continue tinkering for long enough, they will make something great. I imagine that these budgets are going to start shrinking, and it's therefore going to become more and more important for us as data scientists and machine learning practitioners to really prove out our value and clearly kind of explain how we are going to deliver value without ballooning budgets. Here's kind of I think a good theme for kind of going into this idea of thrifty machine learning, that, what we would like to be doing is sowing frugality. And by sowing frugality, what we'll do is we will uncouple ourselves from some of the tools and practices that now constrain our ability to do machine learning and are constraining our ability to do machine learning in a cost-conscious way. And hopefully, if we can kind of sow frugality, we will yield this sort of golden harvest. So let's think about some of my best practices for doing machine learning on a budget. So, when we say machine learning, we mean actually a lot of different things. But let's kind of take a simple case where what we're talking about is supervised machine learning, right? So with supervised machine learning, we have sort of three things we have to do. We need to get labeled training data. Then we need to take the features of that data and do some kind of transformation, some kind of engineering to prepare that raw data for machine learning. And then finally, we have to build kind of some sort of classification algorithm or potentially a regression model that will kind of identify, a relationship, hopefully, between our training data and the labels. So I think that, everybody probably here with us today knows the fun part of this is the classification part. And maybe your second runner-up choice of the most fun part maybe is feature engineering, feature transformation. The least fun and kind of least exciting part of this is that labeled training data part. People don't enjoy labeling data. This is, it's a slow and painful process. Fortunately, I think during the age of abundance, what we saw was this explosion in companies that are offering their services to assist in data labeling. And there actually are a ton of these companies, more than I expected when I started looking, for names and suggestions. There are many, many companies that offer these resources. But what I would suggest is that it's actually better to consider spending time in-house to develop your own labeled data. And I think of this phrase from Candide, the book by Voltaire, mais il faut cultiver notre jardin, right? So we need to tend to our own garden. We need to tend to our own harvest. So, getting labeled data, I think the reason why we would want to cultivate our own garden, we have seen kind of this explosion in commercial providers who do data annotation, data labeling, but it can be quite expensive. So, just for maybe $100,000 labeled samples, you could be paying between $25,000 and $75,000 US dollars. And honestly, as a machine learning practitioner, you probably already know 100,000 samples may not be sufficient to train a robust model, especially depending on how high dimensional and complex your data set is. And so that's really quite expensive for a very small data set. Another thing to kind of think about is what's actually happening at these companies where the data is being labeled. There was this sort of, I think, shocking article. Many people found this article shocking when it came out in 2018. This Alana Samuels article, "The Internet is Enabling a New Kind of Poorly Paid Hell," which exposed that these services, these data labeling services, are actually just employing very low-paid workers to perform the annotation. And so, as you might expect, when you have non-domain experts labeling data, it's likely that the quality of labels that you're getting, especially for more domain-specific data, are not going to be very effective. And when workers are being paid very, very low wages to do this kind of labeling, as you might expect, the quality of the labels are going to vary. And so, this is one place where you might think that you're spending less money by outsourcing this work outside of your company. But that outsourcing work actually can end up becoming a big expenditure if you have to then end up relabeling your data in-house or abandoning the project altogether when you see that there's no signal attached to the labels that you've been provided from this external service. So consider labeling your own data. Here's another place where I think we tend to end up spending a lot more money and resources than we intend to, is this question of, well, which model should I use to build this prototype? And I'm not going to pick on any model type here. But what I will say is that I have observed in my career of doing applied machine learning that people tend to make choices about models in a very emotional way, right? So they frequently select models that they have some emotional attachment to because it's a model that has been successful for them in the past on prior projects, or because it's a model that's kind of attached to some sort of glamour or kind of exciting trend. What I think is that we end up spending a lot more money when we make those model selection decisions in an emotional way rather than a scientific way. And as data scientists, that's sort of where the scientific part comes in. So, what I would say is think about the scientific process when you're doing model selection. And for one thing, consider the context, right? So it's not that a certain model is going to be the best in all cases, probably. A model might be the best for this data set that you're working on or for this problem space that you're trying to solve for in this case. And you can actually test that hypothesis by doing a comparison. Here's a comparison using the Yellowbrick library, doing kind of 3 different classification models on a single data set to assess which of the models performs the best. And, I think it's important to point out that here we see a lot of variation, and we see some cases where there might be some nuance, where even if a model has a very high F1 score, if our concern really is in avoiding false positives, we may actually pick a model kind of on a different basis. So, what I'd say is, do model selection kind of intentionally and scientifically rather than emotionally. So rather than kind of doing what's on the left-hand side of the screen, just Googling what the best model is, actually run experiments like what's on the right-hand side of the screen, where we select several models and then we use the data and some kind of cross-validation measure to systematically determine the model that is best suited to this data set. pick simple models in the beginning and try several in parallel. Identify the ones that are the best and the ones that are weakest, and set an initial baseline. And let that initial baseline help set the ground for hyperparameter tuning, which comes next. So speaking of hyperparameter tuning, this is another place where we spend, as a community of machine learning practitioners, we spend a lot of time and a lot of resources. And so there are a number of different ways to do hyperparameter tuning, whether you're kind of using the tools that are available in a library like scikit-learn, let's say, and doing something like randomized search or grid search, to using kind of a Bayesian search method, some sort of evolutionary method or gradient-based method, or whether you are using, quote unquote, autoML. This is a place where we spend a lot of money, a lot of time, particularly if you're doing what's called autoML, which is honestly really just usually a combination of the other things on this list, but done in a black box fashion, where you have to pay a lot rather than being able to implement some of these search methods on your own, kind of with more intention about how you're executing that search. AutoML tends to be the most expensive of all of these, just because you can't really tell what's happening under the hood. So what I would say is that no matter what type of hyperparameter tuning methodology you're using, remember that search is very, very difficult, and it gets more difficult the higher dimensional your data set becomes. There are many clever optimizations that try to speed up the search process, but then even with those optimizations, there's no guarantee that you'll find a solution. There's no guarantee that, if you do find a solution, that it's the optimal solution. And as your search space gets larger, so as your dimensions get bigger, as you have more data, more features, and more instances, the amount of time that it takes to do hyperparameter tuning increases exponentially. So what to do instead? So if we're thinking about a more efficient way to do a hyperparameter tuning, you might think about, honestly, starting by just reducing your feature space. This can be a way to dramatically reduce the cost of doing hyperparameter tuning. What we're looking at here is a Yellowbrick visualization called the recursive feature elimination visualizer. And this wraps the RFE CV method in scikit-learn. And what it allows us to do is identify the set of features in our data that is necessary to achieve some threshold score, whether that's your F1 score or your coefficient of determination. You might also consider thinking about your train and test data, thinking about how the model changes as you give your algorithm more data or as you take data away. What we're looking at here are Yellowbrick learning curve visualizations for different types of algorithms, for different data sets. And thinking about, what happens as we give the model a little bit more of our data for training. Do we see the training and cross-validation scores converge? Does one drop while the other increases? These are things that can help us make decisions before we spend a lot of time on hyperparameter tuning to kind of reduce that search space and make more effective choices. Another thing that we might want to do is really think deeply about the parameter ranges that we're searching in when we do something like a grid search. For a grid search, what we are doing is we're setting multiple different parameter ranges to explore simultaneously. But oftentimes, before you do that, it's worth it to explore them individually, a single parameter range, and understand what that optimal range is to be searching inside. And that's something that you can do with this validation curve visualization, which is also from the Yellowbrick library. So how to do tuning in a more economical way? Well, first of all, only tune the best performing models. So it's not worth it to do hyperparameter tuning on all of the models that you've explored, only on the ones that are best performing. If you can, do what you can to reduce your feature space, either using feature selection or some kind of feature engineering or dimensionality reduction technique. Make sure you understand the parameter ranges that you're searching within, and you're not doing it randomly. So you're really thinking about what is a sensible range to be searching within. Move towards adding complexity to a model in a purposeful way. So think about whether or not the error is coming from variance or from bias. Think about, if the model is clearly underfitting, that's a good case for adding complexity. If the error is not converging, that's another good reason for adding complexity. So make sure you have a good reason for adding that complexity. And when you do add complexity, do it gradually, and make sure that as you do add complexity through your hyperparameters, that your train and test scores are both increasing. Another place where I'm seeing a lot of teams expend a lot of resources in terms of time and money is with the development environments that they choose to use to do exploratory data analysis and initial modeling attempts. So I'm seeing more and more teams use things like Azure Databricks and Amazon SageMaker as the initial starting point for doing kind of an exploration of the features in a data set and looking at correlations between features and exploring initial models that might be a good fit for the data set. But what I would say is that this is generally not really necessary. So if you consider that those conveniences of being able to use these cloud-hosted tools, they do add convenience, certainly, right? You don't have to worry about configuring Spark locally. You don't have to worry about the Python version that you have installed versus the one that your teammate has installed. That is convenient, but consider whether or not that's really worth the expenditure during an initial prototyping phase. You pay a lot for that convenience. In fact, every moment that those notebooks are running in those cloud-hosted tools, you're paying, or your company is paying. Those are all opportunities where if you were just running those notebooks locally, or exploring, the code locally in a local development environment, you could potentially be saving a tremendous amount of money. And I do hear, there are people who to this will say, well, I can't do exploratory data analysis on my local laptop because I'm working with a massive data set. And in those cases, what I would say is, okay, well, have you tried downsampling? It's actually extremely cheap to just take a very small random sample of your data to perform some initial exploratory analysis. And what you might find is that you can conduct a lot of your preliminary experiments locally before you move things to the cloud. And, I certainly as a applied machine learning practitioner, I understand that, at some point we often do have to move everything to the cloud so that we can kind of have our code running as microservices in a, robust, scalable way. But, that initial prototyping step oftentimes can happen locally. Consider also that, some of the tools that we're using lend themselves to bad habits that give us very limited memory. There's a quote by George Santayana that those who cannot remember the past are condemned to repeat it. For those of us who do exploration in machine learning, I think a lot of times that condemnation manifests something like this, where you'll be working inside a Jupyter notebook. You'll be exploring some models. You've been running your notebook for a while. You have done a tremendous amount of feature engineering and exploration. And at some point, something goes wrong with the notebook, and you're unable to recover some of your data. So whether or not that means you've lost the model or the progress of the model, if something crashed partway through, if you lost some of kind of your intermediate feature engineering components, whether you lost the final model, consider that all of the time that goes into that development has a cost. And there is a cost, aside from just being embarrassed at the end, there's a cost that's associated with losing data. So one thing that I would suggest, and this is something that you can do kind of in the context of whatever your IDE is, whether it's hosted, whether it's local, whether it's a Jupyter notebook or Python scripts or something else, get into the habit of serializing everything. So make sure there are checkpoints in your code where you're serializing not just the model, but any engineered features. So that could be feature vectors, could be embedding spaces, store the stop words that you've identified as being really meaningful in your context for removing things and making sure the important words bubble to the top. You can serialize any lexicons that you've developed, serialize the scores of your models, right? So not just the pickle, let's say, but also the scores that are associated with that saved model. You can also save all of the diagnostic plots that you've done using Seaborn or matplotlib or Yellowbrick. You can save those diagnostic plots to help you remember how the model that you're saving was performing. The other big thing that I see teams sort of forget to do is to serialize and track the training time. So if you end up with two models that perform approximately the same, one of the best ways to pick the one to use in production is the one that has the shortest training time. But if you haven't saved the time that it took to go into training the model, it's going to be hard for somebody downstream or even for you a few days later to remember which of the models was the quicker one. So finally, I think that a big tip for being more cost conscious with machine learning is having a definition of done. This is something that comes from the agile kind of methodology, having a definition of done. I understand that it's much more difficult with machine learning because there's so much unpredictability, uncertainty that comes along with doing machine learning. But with practice, I think that you can start to identify some of these things before you've even gotten started, right? So, is there a certain accuracy measure that you can use as a threshold, even if it's a low one, right? Just one that sort of demonstrates that there is some signal in this data. Or if this is a model that you've been tuning, is there an error bound that you are comfortable with, right? So, of course, if you keep tuning, you'll probably be able to keep reducing the error indefinitely. But, is there a bound where you can be comfortable as a stopping point? Is there some convergence that we can use to demonstrate that we've achieved the initial goals? Or is this modeling effort merely a spike in our sprint? And because the sprint is over, we can close the spike, at least for now, and then decide what to do in our next sprint. And of course, sometimes the project is just due. So be thinking about this definition of done. And, be thinking about how you can practice this, agile methodology in the context of machine learning, where, the goal is to continuously improve, but intentionally improve in the context of sort of structured sprints and cycles, rather than just sort of an indefinite loop where we just try to keep getting better and better and better with no clear end in sight. So in closing, what I would like to suggest is that, our practice in these years of overabundance have led us to the relentless pursuit of accuracy as being kind of the most important thing in all cases, right? Where, there's been, I think, an interest in selecting data sets or selecting projects where that you'll be able to get a high accuracy score, or that you'll be able to publish a paper that shows you can get a little bit higher accuracy score than the last people did. But consider what would happen if we shifted our mindset away from that relentless pursuit of a tiny, tiny bit more accuracy towards model thriftiness, right? So if the goal was, not to beat the last person who was able to train a model on this data set, but instead to have some kind of benefit to your organization, instead, find some way to save time for your organization and keep your organization going during these lean times ahead. Think of all of these new projects that we might work on, all these new things that we might discover if we were able to shift over to this different way of thinking. Thank you very much for coming to my talk, watching my talk, and for considering these best practices and following along on this journey. I hope that some of you will be interested in joining my FAQ session. You can look on the PyData global website to find out when those FAQs will be scheduled, and I hope there will be one that works in your time zone. And if you are not able to attend and you want to connect with me on social, again, my contact information is pretty consistent across all of the platforms. Thank you again, and I hope you have a wonderful conference. Goodbye.